next presentation is called Flight Software and Swarms. It's by Julien Galizzi.
So good morning to all of you. I'm Julien Galizzi, working CNES, the French space agency. And I'm going to present you the flight software architecture and building blocks we are developing to enable future swarm missions. So what are we talking about? For several years, we've been observing in CNES, in pre-advanced studies in phase 0 or A, an increasing number of new missions concepts using or designing multi-satellites that were collaborating. Roughly speaking, to make a kind of photo fit of these missions, we can say that they have from 2 or 3 up to more than 50 satellites. They could be either LEO, GEO, lunar, around asteroids. And most of the time, the aim of this mission is to constitute large-scale distributed instruments. For example, the more dimensioning one, challenging one, was a radio interferometer around the moon, using 50 satellites with, not constantly visibility between the different satellites. Typically, this is, let's say, a preparation activity. So we don't have to launch in the following a tight project schedule within the 2 or 3 coming years. So we have the time to prepare the smart features we need to, to change the paradigm and maybe plan how we could operate and act in such a system. So we need to check and analyze how we can manage the swarm of satellites in a collective way and to manage it from the ground as a single object. We target as much as possible to challenge the level of autonomy, of resilience, and to analyze in detail up to which level we can go from auto configuration capabilities. So now, what we have to check when we have such missions in phase 0, phase A, is what's the readiness level of our technologies with regard to these missions. And most of the time, we were not ready. So we have tried to identify what were the major building blocks where we needed to improve the maturity. Some of them are rather at equipment level, but most of them are rather at software level. So the most emerging one, of course, is the inter-satellite link. So we already have some inter-satellite equipment, but that may not be able to be used inside the swarm of 50 satellites like we have on the picture. Then at networking level, we have to interconnect the inter-satellite network, the TTC network, but also the intra-satellite network. So maybe 3 different physical layers, data link layers, and maybe a networking layer to add in our system. We also need to dive into the swarm autonomy with regard to flight dynamic functions. Most of the time on our missions, we have some, let's say, basic AOCS function inside the satellite, and most of the time we have, let's say, programmation that is sent by the ground to the spacecraft, and then to manage the guidance and maybe let's say, the orbit control. Maybe if we operate 50 satellites, we won't have the bandwidth to send all the telecommands to manage the swarm. All the satellites of the swarm. So we need to shift some of the software functions that were on ground to the board. We need also to assess up to which level we can go for the system resilience point of view. And then, as most of these missions are designed to manage distributed payload, we have to be able to manage distributed payload. So how at software and networking level can we manage and make such distributed instruments possible? And last but not least, do we reuse, let's say, the control centers we have on ground? Do we have to adapt them to manage the swarm? At which level? Here again, we have to challenge things. So this is a flight software conference, so we have to dive into the software architecture now and the test environment. So what was the leading trend of this project? As often, you have already, in the previous presentation, talked about modularity. So we need also modular architecture. So we have some hardware-dependent functions, such as ISL, TTC, GNSS, if we are in LEO, TMHD. But as much as possible, all the software functions, legacy ones, but also new ones, have to be relocatable easily inside the satellite or inside the swarm. These building blocks have to be also multi-mission. So we have seen that we could have missions with only 3 satellites, some with 20 or 50 satellites. Maybe we don't need on a 3-satellite mission the network complexity than for a 50 satellite one. So we should be able to remove useless functions, to simplify complex ones, or rather to optimize complex ones, and change the implementation without breaking everything. So we need a modular architecture with services that are brought to the whole swarm. And some of these functions will be critical functions. So we need to decouple them from the non-critical functions, mainly the payload, for example. So here is the list of the functions we need on each satellite. So these are legacy ones. I mean, we already have them on most of our, let's say, existing satellites. But we have new functions at swarm level. Some of these functions can be hosted on one or more or all the satellites. I mean, will all the satellites will have the TTC communication with the ground, or will we rely only on some gateway satellites to communicate with the ground? We need a kind of network manager to observe and reconfigure the routers. We need a kind of coordinator of the swarm orbit control that will rely on the autonomous orbit control of each satellite. We have some SDIR at satellite level. We will need some SDIR at swarm level too. Maybe located only on 1 or maybe 2 satellites in the swarm. It's the same for the payload. We'll have some coordination and that will rely on local agents. And finally, we'll have a downing manager. I mean, if we have 20 satellites, maybe we won't have 20 parallel stations for each visibility of the antennas on the ground. So we need to assess which satellite has to communicate with the ground, and then warn every satellite to route all the telemetry to the satellites that we talk with the ground. An interesting trade-off that has to be assessed too deals with the use of COTS equipment or optimized integrated architecture. Here is a logical view of the different building blocks we need for our swarm software. In blue, green, we have the functions that are local to each satellite, and in yellow we have the functions that are at swarm level. How can we distribute them across the swarm? One way to do it is to use only COTS components. So I can buy an ESL equipment, I can buy a GNSS equipment, a TTC equipment, whatever. I will buy a platform, legacy one, with its AOCS equipment, with its local SDIR. Okay, no problem. I will have my payload. And I will need an additional computer to host all my new features. I mean, the router to interconnect the different networks, navigation to propagate the orbit in, let's say, in relative or absolute motion in the swarm, and swarm functions. Here, for example, the autonomous orbit control for the swarm. Here, the SDIR for the swarm in the other satellites. But in this case, we have like 7 computers on each satellite. Okay, it should be, cheap. I can buy already existing equipment, but another way to do it is say, okay, I need 50 satellites. Maybe I need to optimize the mass, volume, and consumption of my electronics. Now we have very powerful system on chips, some new RF stocks, powerful, that are able to host many functions. Maybe we can put all these functions together in a single computer and then reduce the mass, volume, and consumption of our electronics. If we have a modular architecture and modular building blocks, we should be able to cover both, depending on our needs. So now let's switch to design choices. You have already talked a lot about modularity. There have been yesterday interesting presentation around time and space partitioning. So what we do is that we use an RN653 hypervisor to run the different applications to have a maximal software decoupling. At the opposite of yesterday, our partitions are not single-threaded. We have guest OSs. In fact, our partitions are virtual machines. We can run in our partitions either bare metal runtimes, either RTEMS, Linux, RN653, RTOS, what you want. So this enables us to have a kind of big flexibility with regards to our dynamic constraints for each of the applications. So using an RN653 architecture will allow us to change easily the location of the function in the satellite or within the swarm, and should consist only in a reassessment of the I/O throughput and latencies that we have in our network, but also managing the memory and CPU spares we have on each computing node. We also use what you may not know that calls LV Fusion. It's our kind of CFS that we have in CNES. It relies on time and space partitioning. So all the green functions you have on the left are generic functions, qualified, it's flying, and so on. And it relies on RN653 hypervisor called Xtratum. That is, let's say, a commercial component that we use on all our missions now. So as you can say, it's designed to supply all the recurrent functions we have on all our missions. I mean, uploading new version software, monitoring control, FDIR, security, and so on. And it aims at be hosted on a system on chip with applicative function will it be payload, AOCS, whatever, depending if you have a platform software or a payload software. So we reused this framework. We pick up all the functions we need, and then we add the swarm-specific building blocks. So clearly, LV Fusion is not, let's say, R&D, let's say, framework. It's let's say, a qualified flying framework, and the swarm currently is still R&D. So we are developing it and going further. Here is a description of the flight software architecture we decided to have. So we intend to have a kind of, let's say, classical platform software, and then to have a dedicated computer that will host all the communication functions, ISL and TTC, and that will host the router function, the navigation to propagate the orbit, autonomous orbit control, and interfaces with the intra-satellite network, and all the swarm functions. If we switch to the network architecture, so it looks like what you have already done with DTN, for example. We want to decouple all the OSI layers at physical data link layers, networking layers, applicative layers. So up to now, we have designed and implemented a kind of IP stack to manage things. But we are assessing if it's the well-fitted network stack or not, and we'll see in the coming months which will be the final software stack, networking stack. Sorry. Now our test bench. We have a simulator that runs on a PC. So we have, like you have, I mean, flight dynamics model, orbital models, equipment models, capability to have to connect the ground segment, but also now ISL models that will model the distances between the different satellites, the antenna lobes for radio frequency visibility, these kind of things. And we have two configurations for validation. The first one is with hardware in the loop. So we use, let's say, a Zing 7000 board to host our software. We have a kind of, let's say, UART links to manage the communication through ISL and NTTC. And the other configuration we have is a full numerical environment where we have the same partitions, the same functions running in a kind of RN6i3 environment, but this time we do not use the binary that we have at that we use on the Zing board, but we rather use a kind of X-Ratum emulator that supplies us the same level of interfaces, configuration, and environment that we have on the real embedded system. So it's a, let's say, time and space partitioning emulator that enables us to compile all our partitions with a native host compiler. And that enables us to have appreciable performances while having still the, let's say, the real flight software. So typically, the one with hardware in the loop is used for, let's say, monosatellite test because it's not easily scalable. And the other one is rather used for the system test when we need to go further in terms of scalability and reach tests with 3 or 20 or 50 satellites. Now let's talk about the new applications we have. ISL is not a new application, in fact, but it's a multi-dimensioning enabler for SWARM missions. The thing is that there is not one single ISL. There can be as many ISLs as needs we have. I mean, which technology will we have? Will it be omnidirectional antennas or directive links? Will it be optical? Will it be radio frequency? Or will it work? Will it allow us to have full duplex communication, half duplex, TDMAs, point-to-point, one-to-N, N-to-N? It depends. So that's an important thing to have in mind when we design our architecture. Regarding the ISL, especially if we are not in LEO, we must use ISL for ranging features. I mean, to know what are the distances between the satellites when we are around an asteroid, for example, to have some kind of relative navigation. So these constraints led us to have the following design choices. First, it's classical, but it's important to say it anyway. We have to decouple the physical and data link layer functions as much as possible from the others using the OSI approach. We need to adapt easily, to be able to adapt easily the ISL properties on the simulator and on the flight software side. I mean, in terms of bandwidth, half duplex, full duplex, and so on. And we already have some proof of concept for ranging when we have no GNSS, but also for collective time functions, because we need to have, let's say, a common understanding of the absolute time across the different satellites of the swarm. From a flight dynamics point of view, the idea is to improve the swarm autonomy, embedding functions that were most of the time on ground. So we'll have, I mean, classical AOCS systems, but that this time will follow onboard constraints. We'll have absolute and relative navigation based on ranging, GNSS if available, attitude from the current satellite, but also this information from the neighbors. We'll have some autonomous orbit control that should include collision avoidance at satellite level, but also at swarm coordination level. Swarm management, so there is not one single swarm management. It depends on the, let's say, distributed functions you have. But the trend is always the same. Improve the swarm autonomy in terms of resilience and optimization. At FDIR level, we need to coordinate the different local FDIR at swarm level. So we need, let's say, a swarm FDIR that will be aware about everything that happens on the different satellites, and that will have the capability to reconfigure either one satellite, either the whole systems, to maintain the system performances at their highest levels. Security and evolutivity, maybe not all the satellites of the SWARM will be launched together. So we need to have the capability to accept newcomers and to reject or even declassify damaged satellites. What are the properties of each satellite? Which function can they host or can they not host? We can also imagine to optimize ISL network performances. Of course, if you have only 3 satellites, you won't have a lot of things to optimize. But if you have 50 with, let's say, a variable connectivity across the different satellites, you need to optimize the path through, let's say, relevant routing protocol. We need also to manage data storage. So payload data, but I mean, for example, if you need to upload new version of your software, you won't use a TTC link to upload 20 times the same version of software. You need some kind of mirroring inside the SWARM. So we have to put all this in place. Optimization for downlink, already talked about this. We have to decide based on different criteria which satellite shall be the next to manage the next downlink, and then tell everybody that telemetry has to be sent to this given satellite. And then we need to manage the distributed computing for the hardware distributed payload. And we may also find new features to implement. Status and way forward. So now we have for maybe 6 or 8 months the first version of the simulator and flight software that run with representative orbits and ISL models. We have our first demonstrations, including routing, ranging, and pruning protocols with 3 and 20 satellites. Network stack selection is ongoing, but we are currently running an IP stack. Flight dynamic functions will be integrated this year and next year. And then we will switch to SWARM distributed system functions. We already have, let's say, promising performances with our SWARM. I mean, with 20 satellites, currently we are running at twice real time. So it's quite interesting to have this in our simulation system. And the idea is that simulator will be used by the new missions in phase 0, phase A, that want to know what they can do with such a system in terms of connectivity and possibility. And that's it. Thank you. If you have some questions.
Thank you. We have one question, or we have 2 questions online. The first question is, does your SWARM configuration pull from existing research optimizing trajectories based on connectivity and mission requirements? If so, could you please elaborate on the novel features in your approach?
No, we don't. I mean, not yet. We have to, it's quite, for example, rather a kind of bottom-up approach, starting from high-level needs.
The second question is, where does the time source for the ranging timing functions come from?
If we don't have GNSS, it will be a kind of, I know the word is the correct one in English, kind of barycenter of the different local types.
I think software people like slacking their questions. So I think everybody's using letting it. They don't want me walking around.
I have one question. On the slides where you're showing a rectangle around portions of the software. Are those your ARINC 653 partitions?
Yes.
Okay.
It's all partitions. Thank you.